Hi, welcome to Computing Foundations, a channel for beginners who want to learn about computers, programming, and the math, science, and art behind the field. I'm Josh, a retired software engineer. Please subscribe, like, and share your comments to help us improve the channel. Okay, today's video is actually a post-mortem for our '07 challenge. So after we finished the flow of control lesson, I gave you a challenge. And if you look in the file 07-challenge, you'll see a working implementation of the program challenge, which was to find all of the prime numbers from 2 up to about 4 billion. So let's take a look at how I solved this. Let me get rid of that for you. All right, looks good. So here's our challenge. We want to write a program that will count the quantity of prime numbers between 2 and 4 billion. And I gave you a special note here that this special number, this 4 billion number, is the maximum value that can be stored in an unsigned integer. That is a 32-bit unsigned integer. So here's what my solution looked like. I declared two variables at the beginning here. One of them, an unsigned integer where I was going to count the number of primes. Now this doesn't really need to be unsigned necessarily because surely there aren't that many prime numbers, but I went ahead and declared it as an unsigned int. So this means if potentially every single number between 2 and 4 billion is a prime number, well, I'll have enough space to count up that high. And then I also created an unsigned integer to store what is the largest prime number that I end up finding in that range, because I thought that would be kind of interesting just to see, what is that large prime number. All right, next thing I do is I declare a variable for the maximum value that I want to search. So I just set this to be the largest value that can be stored in an unsigned integer. So this variable now, the variable max, is holding the largest possible value an unsigned integer can hold. The next thing we do is we start a loop, which is what we learned about in our flow of control class. This loop is initialized with an I variable that is an unsigned long. Why did I make it an unsigned long? Well, if you look at the way I've constructed this loop, I need to check values of I all the way up to equal to the maximum value. And I've already said this maximum value is the largest value that can possibly be stored in an unsigned integer. So if I only made I an unsigned integer, it would never be able to be greater than max. It would just roll over back to 0 once I got to the max number and I incremented it, it would roll over to 0. The loop would never end because I would never be greater than max. It would be impossible because the value I would only be able to hold numbers up to the maximum value. So we defined I to be an unsigned long. This is important, and it might have been an early error or an error that exists in your program that you didn't think about. So make sure that your counting variable can get to a large enough value that you can stop your loop, basically. All right. Next, I declare a variable called isPrime, and I set it to 1. My thinking here is we're just going to assume that the current variable I is a prime number until we can prove to ourselves that it's not. So that's the approach I'm taking here. All right, the next section here, section 57 to 61, this is totally optional. What I did here is because this program needs to run for quite a long time, I wanted to have some indicator on the screen of how much progress I was making, so I would have confidence the program was doing something. So what I do is I take the modulo of I, that is, I take the modulo of I by 10,000. So every 10,000 numbers I am going to clear the screen and print out a message that just says, what percentage complete am I? So to know what percentage complete I am, I divide I by the maximum value that I'm expecting to be able to store. So here you can see that I cast both of these as doubles so that this is a floating point division. I just want to make sure I have plenty of space and precision to hold the two numbers. So I use a double, I convert these to doubles before I do the division. This weird command here, I describe it up here in the comments, is just necessary to flush the output to the screen. Sometimes when you're clearing the screen, your output will get lost if you don't flush it out, but that's not that important to understand why that happens, but that's why the flush command is there. All right, so once again, 57 through 60, completely optional. All right, now I come down to 84. We're inside of our initial for loop, which is looping through all the integer values from 2 to 4 billion. And inside, for each value of I want to run another loop. I create an unsigned long j variable that's going to go from 2 all the way up to the square root of I. And it's going to check to see if any of those numbers will divide evenly into I. So here I check to see, is I evenly divisible by j? And again, j will be from 2 all the way up to the square root of I. If I find that it is evenly divisible, I set is prime to 0, meaning false. This is not a prime number. Okay? And then I break out of this for loop. The break command will stop the for loop. It won't continue to advance. It'll just end the loop, and out I will come to the next line, which is line 97. In line 97, I check my variable, my success variable, to find out, hey, that number that I was just looking at, did it turn out to be a prime number or not? If it is a prime number, I increment the number of prime numbers that I found by 1, and I store that number. In this regards, as I'm going through all the values of I always store the last prime number that I found, the biggest prime number I found so far, into the largest prime number variable. And then finally, I have a print statement that will write out to the screen, hey, between the value of, that was an error, between the value of 2 and max, which is 4 billion, there are however many prime numbers I found. And the largest prime number is, and I write out the largest prime number. Now, this application on my computer, I'm working on a MacBook Air, which has an ARM processor in it. It did take several hours to run this. So one way you can shorten the program is just change this variable on line 24 to be a smaller number. And the program will run a lot faster because you don't have as many things that you're going to be checking. But I do think it's fun to kind of push the computer to the limits and verify that your program will work at these large integer values. Because if you didn't define all of your variables to be the correct types, your variables might run out of space. And remember, when I reach the largest value that a variable can hold, if I try to add more to it, it just rolls over back to 0. This is called an overflow of the value in the variable. And that can cause your program to just go into an infinite loop where it never ends because it's always coming back to 0 before it reaches the maximum value that you're targeting. So hopefully this was a fun challenge for you. If you didn't come up with a working solution, don't stress. The most important thing is that you tried to solve the problem and that you thought about it long enough that now that you see the solution, you can kind of appreciate where your thinking was not quite right, what you need to change about how you were approaching the problem. As you continue to do this, you're going to get better and better. So thanks again for tuning in. I hope you enjoyed the challenge, and we'll see you next time.